Can you hear me? Can you hear me? Oh, I think that's working. Oh, there seems to be a delay on the audio, I think. So, does anyone actually have any questions that we can get started with? Waves is a nice easy place to start. Let me see if I can get the graphics tablet working a moment. Give me a moment, I'll find the pen and then I'll see if we can sketch up some stuff on the screen. They're known by both stationary and standing. No, the tablet's acting up a little bit. Let me see if it will stretch enough to where Right, we're starting to get somewhere. Um, had to stretch a few wires out. I think we're about ready to make a start. Oh, cool. That's gone into a new layer. Right. Let's erase all of this. So, standing waves and stationary waves. They are synonymous, known two different names to describe the same phenomenon. They occur due to the interaction of a pair of waves. Where's my pen gone? There. A pair of waves which are travelling in opposite directions, and under ideal circumstances these will have the same frequency, which equivalently means the same wavelength, and they will also have the same amplitude. Ideally, we can get a degree of standing waviness even if two waves don't have the same amplitude. But ideally, both with the same amplitude. So, if we have a look at working, working on that half. I see what it's doing. No, the tablet's still acting up a tiny bit. Right, okay, we'll have to bear with it. So we take two lines like this, and these are the end of our wave. So our wave stretches between here. This might be on a piece of string, for example, or it could be in a tube, but this flat line just represents our base wave, our base medium that the wave is being carried through. So this could, for example, the string or the tube or whatever. And then what we can do is, using this, we can represent amplitudes on this. So if I were to send a wave along here, something like that, that's representing the displacement of the wave at any given point along this, for the sake of argument, we'll stick with it being the string. So we've got this piece of string here, and as this wave travels along it, so with the way I drew it, we can have it traveling in this direction towards the right. When it hits the other end, over here on the right hand side, it's going to get reflected, and so then the same wave is going to be reflected back towards the left hand side. As a result, we've got two waves in the same place at the same time of the same type, so we will have superposition going on. As a result of this, when we have superposition, the resultant wave is determined by the sum of the amplitudes of the component waves. In this case, we've got two waves traveling in opposite directions. Because they're traveling in opposite directions, their phase difference is constantly varying. And that means that at some points in time, the waves are going to be in constructive interference. In some places, they're going to be destructive, which gives us our standing wave pattern. And there's a really nice diagram which exists on Wikipedia, to save me writing all this out again, which is this one here. So you can see here we've got two waves. So there's a red wave and a blue wave. If you can't quite make it out on the stream, you might want to pull up the Wikipedia page for standing wave, and you'll see this diagram. I trust this is all streaming okay. Nobody's said anything in a while. Turn my audio back on. I muted myself so I wasn't hearing myself with a delay. Oh yes, that seems to be working. So we've got the blue wave and the red wave, which are traveling in opposite directions, and we've got in this diagram the black wave, which represents their superposition, the sum of the amplitudes. As they travel, we can see at this point they're in phase. Down here we've fallen about a quarter of a wavelength out of phase, and so you can see the black wave, the resultant wave, is a little bit smaller. Here the waves have now fallen into antiphase, so we can see the peak of the blue wave lines up with the trough of the red, and vice versa, which means our resultant wave is zero, nilch, nada. Down here, they then carry on traveling past each other. Oh, that's a good question. And then they're falling back into phase again, and we get another set of peaks. And we can see these dashed lines represent something important. Let's look at this middle large, this left-hand large dashed one. We can see up here, at this point in the cycle, this corresponds to a point where this black wave has got a very large displacement. Down here, it's still got a large displacement, but it's in the opposite direction. If we look at one of the finer dash, we can see here there's zero displacement, here there's zero displacement, here there's zero displacement, and so on for the subsequent ones. So we can see that there are points in the standing wave which always have zero amplitude, and these are called nodes. We then have points which have maximum amplitude. Now at times they will have zero displacement, but their amplitude, which is the maximum displacement, will be the largest at these antinodes. And so these pattern of nodes and antinodes are one of the key characteristics of a standing wave. There's a question here: is superposition and interference the same thing? As far as we're concerned, they're kind of describe the same thing, but the interference tends to be a little bit more tends to produce slightly more interesting effects, and we get onto that when we're looking at diffraction patterns. So superposition of waves, we're just describing when we've got two or more waves of the same type in the same place at the same time, then the resultant displacement will be the sum of the individual displacements. When we get interference, it's a similar thing going on. We've got waves adding up, and at different places they will have different phase differences, so they will be either constructive or destructive interference, but we tend to use the word interference to describe when we're talking about diffraction patterns, for example from diffraction gratings or from the Young double slits. So that's the difference between superposition and interference, and that's a brief introduction to standing waves. Oh, there's a little question there about harmonics as well, which is really nice. So let me go back to this diagram. Let me clear it out again, and we can have a look at what we mean by different harmonics. So we can see for a standing wave to form here, if we've got a string which has got the two ends fixed, those two ends can't move, and so those two ends must be nodes. So if I sketch this out again, but I'll label it a bit different. There we go. So I've got 2 points here, one here and one here. These are the ends of our string, and because these are fixed, they must be nodes. So I'll use this tablet in a little while. So I've labeled them as N for nodes. Because we can't have two adjacent nodes, we know there must be at least one antinode in between. And so we can use that to work out what the fundamental pattern is going to be. So we're going to have a nice curve here where we're going to have a peak in amplitude at the A for antinode. So we're going to have, so we would have a peak there and something like this. This is what we call the fundamental mode or the first harmonic. We can then have a look at what the next one would look like, which is still going to have a node and an antinode, a node at each end rather. And this time we're going to have not just one antinode in the middle, but the next pattern is where we have one extra node antinode pair. So each time we go from one harmonic to the next, we're adding in one more node and one more antinode. And we want to space those out evenly, making sure that a antinode has got a node on either side and the node has got an antinode on either side. So here's our antinode. We'll have a node in the middle and another antinode here. And we can see that's spaced out evenly. So we've got antinode, node, antinode, node. But the only difference between this and the previous one is we've added in one extra antinode and one extra node. So here we have two nodes and one antinode. Here we've got three nodes and two antinodes. And then once we've got this pattern of nodes and antinodes, we can then sketch in what the rest of the waveform is going to look like. Once we've got the waveform, we can start working things out from it and measuring it. Oh, hang on, there's another question come up. Can we say constructive superposition instead of constructive interference? Because my teacher kept on using superposition rather than interference. Okay, what I would say to that is it's going to vary a little bit by exam board. If you're on the OCR exam board, my experience would suggest that constructive superposition and constructive interference are synonymous. But if you're with an exam board that is not OCR, then the exam board might be a bit more picky about the phrasing. So I would suggest listen to what your teacher suggests, but also have a look at some of the past papers. So if you look up a past paper which has a question asking you to describe what superposition is or describe the formation of standing waves or interference patterns, then once you've found that question, you can look at the mark scheme and you can see what the mark scheme offers as guidance as to whether or not superposition and interference can be treated as interchangeable. Right, so back to this. We can now have a look at making some wavelength measurements. So we can see we've got this pattern. If we go between adjacent nodes or adjacent antinodes, then that is equivalent to a half a wavelength, or lambda over 2. So this second harmonic, the length between the two ends, is going to be equal to one wavelength. In this first harmonic, the fundamental, the length between the two ends is going to be equal to a half wavelength. So if this length was, just to choose something at random, 15 centimeters, then the fundamental mode, we could work out the wavelength. We know that a half a wavelength is 15 centimeters, which means one wavelength is going to be 30 centimeters. If you look at the second one, we've got one wavelength is 0.15 centimeters, and so that makes it nice and easy. The next harmonic you'll hopefully recognize looks something like this. Now imagine this coming out to the end. So we've got a node here, one here, one here. So again, we've just added in one node and one antinode. Like that. Sorry about that, I've got something in the oven. Um, it's just one more node and one more antinode to form this harmonic. And this harmonic, we can see we've got 1, 2, 3 halves of a wavelength. So we've got 3 halves of lambda, 3 over 2 times lambda equals 0.15 centimeters. So that's going to give us 3 lambda is equal to 30 centimeters. We can then divide by 3, and that will give us lambda equals 10 centimeters. So we can use this to work out the wavelengths. If we were then provided with a wave speed or a frequency, then we could work out the other using the wave equation. So V equals F lambda. So if we were given, having worked out the wavelength, we could, if we were given the frequency, work out the wave speed, or if we were given the wave speed, work out the frequency. Bandwidth, asked Jack. What is bandwidth? That's something beyond the scope of the course that this stream is aimed at. So that's not something I'll be commenting on. If that's something that's included in your course, then you'll need to ask your own tutors about that or ask Google. But that's beyond the scope of what the course that this stream is aimed at. This is aimed at A-level physics and especially the OCR course. Are we okay with standing and stationary waves then, or do we have any more questions about those, or any further questions about any other topics that we'd like to launch on? I saw Archie was there at the beginning. I don't know if he's still there. I guess Archie might have some questions about the second year of the course if he's still there, which we can address. At the third harmonic, lambda equals 2L over 3. Yeah, that's what we've got in the bottom right-hand corner here. So this 0.15, that's the length that we've got of our string. We just chose a value to put in there, but that's equivalent to our L. We can see this 3 halves lambda equals L is equivalent to saying lambda equals 2L over 3. If you rearrange this, you would get to the form that you were provided. So rearranging this would give us lambda equals, if we bring the 2 up, 2 times 0.15, which is our L, over 3. So then divide by the 3 to move that over there. But a better way, trying to remember that at the third harmonic, this is the relationship between wavelength and length, and so on. It's better to be able to have a look at the patterns and recognize this pattern is this many wavelengths or this many halves of wavelengths. So in this case, 3 halves of wavelength, and then set that equal to the length, and then you can rearrange that with some simple algebra. Polarized light, that one's a bit more interesting. Let's have a look at that then. Again, there's a quite nice picture on Wikipedia somewhere, I think, if I can pull up that page we had. Yeah, here we go. Let's have a look. Actually, I think it's on Commons. I don't think it's on the Wikipedia page. Right. That one, oh, that was quite nice, but it's been drawn a little bit confusing. Where's it gone? Here we go, this one will do. So we start off with unpolarized light, which must be a transverse wave in order to be polarizable. So something like something like sound waves would not be polarizable because it's longitudinal. So when we talk about polarization, most of the time we're talking about parts of the electromagnetic spectrum. So we can polarize visible light, and that's useful in sunglasses, for example, or sometimes used in photography. We can polarize also microwaves and radio waves and things like that, and that can be useful for part of filtering. So you can see in this diagram the wave is traveling from left to right and going backwards a little bit. And we start off with it unpolarized. So the reason that transverse waves can be polarized is because they oscillate, because their displacements are perpendicular to their direction of travel, and we live in a 3D world. They can either be oscillating up or down as they move forwards, or left and right as they move forwards, or something in between, so like diagonally. So we can see in this diagram we've got up and down, we've got left and right, we've got diagonally as well. And so unpolarized light is made up of light waves oscillating back and forth in all sorts of different directions. What we can then do is pass it through a polarizing filter. So we can see here we've got a polarizing filter, which is represented by these vertical slits. And these slits aren't small enough to be producing any diffraction, so we're looking at these slits separate to the diffraction. If this was something like visible light that we were trying to polarize, then these kind of effective slits are just produced by something on a molecular size inside a filter, rather than being visible as slits like you might get in a diffraction grating. If you've got a microwave polarizing filter, then a few metal bars will be sufficient, and those you may have seen in a lab exercise that your tutor may have done with you. Anyway, so on passing through this filter, we can see because of the arrangement of this filter, it's only going to allow waves which oscillate in one direction to pass through it. So on passing through, we lose that option of oscillating up and down, or left and right, or diagonal. Only the ones which are oscillating in the correct direction will be able to pass through the filter. And so when we look on the far side, the light is what we call plane polarized. It's polarized into a single plane, or a plane is like a flat shape. So you can see this part over here is just oscillating within this 2D rectangle, so within this plane in that single direction, so it's plane polarized. Any further? Dear, it seems I may have put you to sleep. It'd be nice if some of my own students would turn up, but never mind. Mechanics and suvat, yeah, that's part of what Unit 1 in our course. So we can have a look at that. Did you have a specific question? Or did you want a whistle-stop tour of suvat and a quick reminder of how that all works? Oh, we've got two requests there. Let me start with the bit on suvat and projectiles, since that got in there first, and then I'll move on to diffraction gratings after that. Um, so if we have a look at a projectile, that typically starts with us having something launching at some velocity, at some angle, generally labeled theta, above the horizontal plane. And we might be asked to work out how high it goes, or how far it goes, or how long it's in the air for, or something like that. And we can do that using suvat. So let me take a slightly simpler example to begin with. Let's say we just had a ball and we dropped it. We could use suvat to work out how far it went after some time, or how long it's going to take to fall some distance. And so a nice way to do it is to write out our 5 suvat variables, work out which ones we know and which ones we want to know. So let's say we know our distance is h, and we want to know how long it takes to fall. So if I drop it from rest, then our u, our initial velocity, is going to be 0. We know our acceleration is going to be minus 9.81, so that's g. We know the distance traveled is h, and we, in this case, want to know what the time is going to be. The final velocity we don't particularly care about in this question. In a different one we might want to know it, but in this one not so much. Now that we've got 3 variables identified and we want to know which one we want to find, it's simply a case of picking the appropriate equation. So in this case it's going to be s equals ut plus a half at squared. So that contains su, a and t. So the one that we don't care about, we want to put the equation that doesn't have that. So s is ut plus a half a t squared. And in this case, because u is 0, this is going to simplify to a half g t squared. So I've replaced the a with the g, and it's our h that's equal to this. We can now rearrange this to work out our time. So we would have t is equal to 2h, so that's timesing by 2, dividing by g, and then take the square root. So 2h over g, all rooted, would give us our time value. So that's a ball dropping vertically. If we had a ball which we were just firing horizontally with a constant velocity, so maybe not a ball, that might be like a car traveling along a road at a constant speed, then we could use that to work out how far it travels in a given time. Now when we're talking about projectiles, all we're going to do is both this at once. So let me clear off this mess a little bit. The key to projectiles is remembering that the vertical and horizontal components are completely independent, except time. So when you're presented with a with a projectile, we're still just going to write suvat out, and we can work out what we want to know, what we already know, how we can work out any gaps, except we're going to write it out twice. One is going to be for the vertical, so I'll use a subscript v here. And one of these is going to be for the horizontal. So that's a little h there for that one. So we can have a look at the question, have a look at what we're provided, and see which of these 10 quantities we know. Now typically we wouldn't be given the time. Most of the time the acceleration, when we're looking at projectiles, is just going to be g vertically and nothing horizontally. But I have seen a few questions where maybe you're on Mars, or maybe there's a really nice one, I can't remember where it's from, but with a paper aeroplane, and you're asked to work out its lift force, so what force it's got holding it up, and that force reduces the acceleration, so you actually need to find the acceleration from what's provided there. But so the S, U, V, and A are going to be completely independent for these, so the speeds are going to be independent as well. From this V speed V fired at angle theta, we could work out the initial vertical component, so that's U, V, and we could work out our initial horizontal component, so that would be U, H, using, in this case, cos theta to find the horizontal and sine theta to find the V. But that key about the times not being independent means that if we know one of these times, we know the other. So maybe for horizontally, for example, we need to know the time, but we don't have enough quantities here to work out what it is. If we can work out the time vertically, we can use that time over here. So for example, if we want to know how far we've got to go, or how far this projectile goes, we know our initial vertical component. Let's take our acceleration to be 0. Because our acceleration is 0, we're not actually going to need to use any of the more complex suvat equations. We can just use S is equal to ut, i.e. speed is, distance is speed times time. But we don't know the time. Fortunately, if we can work out the time over here, that's going to be equivalent. So if we were just looking horizontally, there's no way to find this time and solve the question. But if we know any of these three, so if we knew our initial velocity and our final velocity and our acceleration, or the displacement and any two more of these, if we know at least 3 of these 4, then we can find the time. We can put the time in over on the right hand side, and then we can put that into here, and out pops our question, our answer for how far it's gone. So that's the sort of approach I would use when looking at projectiles. I'd write suvat out twice, one set for the vertical components, one set for the horizontal components. I can then work out which ones I know for each of them, and remember that the time must be the same for each of them. But everything else is going to be independent. Then you can just start working out components from the velocity to fill in values. You can start picking out suvat equations to calculate values, etc. So hopefully that's a nice recap on how we can use suvat in projectiles. Next, I guess we'll have a look at diffraction gratings. So before you start worrying about diffraction gratings, you need to make sure you're comfortable with the young slit apparatus. So how, let me clear this out. So in a young slit we've got coherent light, coherent meaning a constant phase relationship. And that coherent light is fired at or passes through, is U normally 0? That very much depends. So we can see in the question we had up a moment ago, the initial velocity is going to be non-zero. So both the initial vertical and horizontal components would be non-zero. Let me see if I can undo. There we go. So this vertical component is non-zero, this horizontal component is going to be non-zero. The only time that either of these initial velocities is going to be equal to 0 is if this ball is launched entirely horizontally or entirely vertically. So if we had some question we get sometimes is if you've got like a table or a cliff and something is knocked off the edge, it's not got any initial vertical velocity. It's going to have an initial horizontal velocity as it comes off here, but its initial vertical velocity is 0. Alternatively, if you're going back into 1D, so just an object falling, rather than involved in 2D projectile motion, then sorry, I got lost there reading the comments a moment. Where was I? Things coming off. Oh yeah, 1D motion. So if we've got 1D motion, then if we drop it from rest, so if we've got our ball, if we release it, if we just let go, then initially it's not going to have any motion, so its initial velocity will be equal to 0. Alternatively, it could be launched upwards, so it could be just a ball that's been chucked up vertically or been fired downwards. That would give it a non-zero initial velocity. So I would say no, U is definitely not normally 0. But there may be things in the question which indicate it's 0 rather than explicitly saying. So you need to read questions carefully. Phrases like released from rest mean that initial velocity in at least one of the dimensions, either vertically or horizontally, is going to be 0. You wouldn't necessarily be told U is equal to 0 in this case. You wouldn't necessarily be told either, for example, that the acceleration is equal to g. You might just be told it's in free fall in Earth's gravity. And so you recognize, even though you're not explicitly told anything about acceleration in a question, it's up to you to recognize that the acceleration there will be equal to g. Right, back onto Mohammed's question about diffraction. So we're okay with young slits, but we're a little bit confused about the angle. So let me clear this off again, and we can have another bash at that. So we've got our diffraction grating here, very crudely drawn. We fire some light at it, and then if we look at the screen over here, we get a couple of bright spots. So if you've done this in the lab, you've probably done it with something like a red laser, and so you'll have a series of spots appearing on the screen, something like this. Now this is slightly different to what you get when you had the young slits. So if I label this D for diffraction grating, and I add a Y here, we can have a look at what we might get for young slits. In the young slits, we tended to get less discrete points. We got quite feathered fringes compared to the very discrete dots that we get in the diffraction grating. Again, if you've done this as a lab exercise, you may recognize this. So we get things that's been smeared out, and it's sort of quite bright in the center, but then fades out. It's a bit hard to represent that here. I don't know if this has got like a smudge button or something. So we would get quite broad fringes in each of these locations rather than discrete dots. And because those are broad fringes that are spread out, it makes it harder to easily measure distance between the fringes. So our equation, so in the young slit we can use a nice equation like if this is our screen distance, this has wavelength lambda, we have slit separation x, and we have so fringe separation x and slit separation a. Then we get a nice equation which comes out something like, let's see if I can remember which way around this is, lambda equals ax over d, I believe. And so we can use this to measure lambda if we know d, we know a, and we know x. But it's hard to measure x accurately because these fringes are so spread out. When we use a diffraction grating rather than just two slits like we do with the young slits, rather than getting these spread out fringes, we get very discrete points as illustrated earlier. And so because we've got these discrete points, it makes it much easier to measure the separation between the points. So the advantage of using a diffraction grating over young slits is that we can take much more accurate measurements in order to work out the wavelength value. So then the next bit is to look at the maths. So when we looked at the young slit equation, we looked at the separation between these fringes. When we do the diffraction grating, rather than looking at the separation, we look at an angle. So this central spot, if I reposition this line a little bit, this central spot, if that's straight ahead, so imagine if there was no diffraction grating in front of this laser, then that laser would produce this single point here. But because it's passing through the diffraction grating, we get these additional bright spots. And when we're looking at the diffraction grating, the maths looks at what's the angle between this first bright spot and each subsequent one as an angle from where the slits are. So we can see this means that for a given angle, if the screen is nice and close, then these fringes are going to be very close. If this screen is far away, like on the other side of the lab, then the fringe is going to be more spread apart. You can see that represented up here. These two lines are quite close, over here quite far apart. Now the mass we get here instead is, I believe, it comes out as n lambda equals d sine theta, where in this case lambda is still lambda, n I'll come on to in a moment, and this d, rather than being this d, that's what we refer to had down as a when we were looking at the young slit. So within the textbook and within the formula sheet, for example, it uses a different letter in the young slit and the diffraction grating to represent the same thing. That is the separation between the slits in the grating, or between the pair of slits in the young modulus experiment. And this theta is this angle here. This n is described as the order, so the order of the fringe we're looking at. So if this is n equals, we would generally take that to be 0. This would be 1, 2. This would also be 1 and 2. So the angle between the central maximum and the first fringe, it can be worked out by setting n equal to 1. Between the central maxima and this next fringe could be worked out by setting n equal to 2. Then if we know lambda and d, we can find theta. If we measure theta and we know d, we can find lambda, for example. However, if we were to be given data between this pair, our n value is going to be 2. So although this is between the first order bright spots, because we're going from the first order to the central and then out again, n is actually going to be equal to 2. So a better way to look at n might be to look at how many gaps have we got. So if I'm going across one gap, n is equal to 1. If I'm going across two gaps, n is equal to 2. So if I were to go from this spot to this spot, I would have n equal to 3. And that would allow me to work out the angle between those. So what I can do with this is I can set up this display, measure the distance between these as an angle, and then that will allow us to take very accurate measurements of lambda, because these small spots can be measured very accurately. Hopefully that clarifies a little bit on your diffraction gratings. Make another comment. If there's something you're still unsure on, if that's just completely bamboozled you and made it even worse, perhaps. Yes, D is the size of the gap. So, or rather, not the size of the gap, but the separation between the slits. So in this diffraction grating, what we've got is a set of vertical lines, like that polarizing filter we had earlier, only much larger. But what was in that diagram is a nice illustration of it. And D is how far it is between each of these lines, or between each of these gaps in the diffraction grating. Now, what tends to happen is, rather than being told there is like 1/10 of a millimeter between these, what you tend to see is this would be in a screen, and this screen would be labeled something like 300 lines per millimeter. And in this case, we would then have to use that to work out what our D value is. So our D is the separation between the lines. So if we've got 300 lines per millimeter, the separation between the lines is going to be 1/300th of a millimeter. So that's going to be so 1/300th of a millimeter, which you then probably want to make sure you turn into meters to avoid power of 10 errors. Oh, don't do the sir thing. Do I have a video on this topic on the channel? I don't know. You're free to have a look. I kind of petered out a little bit towards the end of Unit 2. I got a bit busy when I was going through them, and I haven't got round to catching up. I'll have a quick look, although I mean you're just as capable of looking up. There's a video called Diffraction. Actually, that's probably not going to be it. That'll just be on general diffraction. No, it doesn't look like there is. I'm sure if you ask YouTube in the search function, you can probably find a few more videos on them. There's plenty of other tutors and people who have been doing videos like this. I'm pretty sure I've seen one or two others specific to the OCR spec as well. So if you stick OCR diffraction grating or OCR interference patterns or something like that into the search, you can probably find something that somebody else might have done. I'm sure you're too kind, but there we go. Yes, I have heard some positive comments. It's been on my to-do list for about a year or two to finish off the rest of the spec. But I think they're going to change the syllabus in a year or two, so I'll have to do them all over again. But you're probably not interested in that. You'll be at uni by the time they do that. Resistance, the big equation with V in equals sum in V out. Sum in. R, as in, not as in sum of those going in, as in something spelt really poorly, I'm guessing. As in V in equals something V out. Right, okay. What you're discussing there is potential dividers, which is a really posh way of saying two resistors. So let me sketch out a little diagram. Let me see if the pen's working any nicer now. I've been using the mouse for a little bit. Whoops, no, that's definitely not working very well. What's that doing? Okay, that's just done something weird. Let's try that again. Right, here is a cell. And this cell is going to be connected to, oops, stick to the mouse, this pad's acting up. This cell, or battery, or whatever you want to call it, is connected to a pair of resistors. And we will label this R1 and R2. And this cell, we will label it as having a voltage VI for V in. And what we can do is have a look at what would be the voltage across any one of these resistors. Now we'll just start by having a look at what that value would be, and then we can work out why this is of interest. We'll have a look at a couple of practical examples because that's something that sometimes gets asked. What's the best way to derive this? So we know V is equal to IR, which is Ohm's law. And so we can use this to work out what the current would be in the circuit. So our VI is equal to the current times the sum of the resistances, so R1 plus R2. And then we can now use this current value, so I equals V in over R1 plus R2. We can put that back into this equation, so to work out the voltage across resistor 2, that's going to be this current, so Kirchhoff's law tells us this current is going to be the same everywhere in the circuit, so the same through both of these resistors and the battery, is going to be equal to V in over R1 plus R2. That's our current, and then we want to times it by our R2. That will tell us the resistance across that. So we can see that the V out, or in this case we've labelled it as V2, is equal to the voltage going in times R2 over R1 plus R2. If we wanted to know the voltage across V1, then all that's going to change is this resistor. So V2 is VI R2 over R1 plus R2. V1 is VI R1 over R1 plus R2. So that's how we can work out what the voltage is across these. And you can see this shows if R2 is much larger than R1, R1 becomes kind of like nothing. And we get R2 over R2 which is 1. So if R2 is much larger than R1, it takes pretty much all of the voltage. If R2 is very small compared to R1, then we're timesing it by a negligible value and dividing it by a large value, so the voltage across it will be very small. If we've got something in between, we'll have something in between. So the voltage divides across these proportional to the resistance. The larger the resistor, the more of the share of the voltage it will take. So we can use this to split voltage across two things. So let me give you a couple of examples. If one of these, we now make a variable resistor. By varying this resistance, we can vary the voltage here. And so if we replace this voltmeter with something like a diode, in fact, let's do that. So we replace it with a diode. And we also stick an ammeter in there. Then by varying this resistance, we vary the voltage that's going to be across it. And the voltage across this resistor must be the same as whatever is across this branch. And that's due to Kirchhoff's voltage law. A third resistor I'll look at in a moment. So this example here with the diode, by varying this we can vary the voltage across it and we can measure the current at each point. So this would allow us to plot a voltage current graph for a diode, or if we replace the diode with a filament lamp, then we can measure the voltage current graph for a filament lamp. Another nice use might be our voltage input might be coming from a sensor, for example. And our sensor might put out something in the range of 0 to 10 volts. So this might be sensing the temperature and turning that temperature into a voltage value. And we want to record that by feeding that into a data logger, but our data logger only reads from 0 to 1 volt. So by putting this across a potential divider, if we have say 9 kilo ohms and 1 kilo ohm, then the voltage will divide 9 to 1. So the voltage across this will vary from 0 to 9 ohms rather than 0 to 10, and the voltage across this will vary from 0 to 0 to 9 volts. The voltage across this will vary from 0 to 1 volt. So a potential divider can be used to scale down a voltage if this is a fixed resistor, so we can use that to feed into something. Epic's question, Epic edits by SAS. What's SAS short for, I wonder? What if we've got a third resistor? So let's have a look at that. Because the problem with potential dividers is that when we connect the output to something, it can affect the potential divider. So if I connect a resistor here, this is going to affect this circuit. So in working out what voltage goes across here, it's not just R2 that's going to affect this. It's the voltage of this whole, the resistance of this whole section. And we know that when we add a resistor in parallel, the resistance drops by an amount which is going to depend. So if this is a very large resistor, so something like 1 mega ohm, then the effect on that this has on the resistance of this section is going to be negligible. And so the potential divider will continue to function as expected. If this is something very small, like 1 ohm, now the effect is going to be quite marked. So if we put a 1 ohm resistor in here, actually the resistance of this section is going to drop down to about 1 ohm. And so now this section has not an overall resistance of 1k, taking 1/10 of the total voltage. It's got an overall resistance of about 1 ohm, taking about 1/9000th of the resistance, of the voltage rather. And so when we put a load on the output of this, we need to take care and make sure that what we've got on that load isn't going to affect the circuit and affect the way that it's divided. And that's what you were getting at with your issue of three resistors. If you had three resistors all in series, then the maths we've done on the right hand side extends, and we just get a plus R3 going on this section when working out the current, and on the bottom we'd have a plus R3. And so the voltage gets divided across three resistors instead. Typically you'll just see this discussed in the context of just the two resistors. If your question about having a third resistor in parallel with one of them relates to a specific exam question, maybe, I'm hypothesizing until the stream catches up and you can comment. Then you can tell me which paper and which question, and I can pull that up on the screen and we can have a look at that together. That's doable. Oh, we don't sit on. In your own time there, dearie. If you've got the question paper in your hand, then usually there's a copyright thing in the bottom left or bottom right hand page, bottom left or right hand side of the page, and that'll say like copyright OCR 2010 or 2011 or whatever, and that tells you which year it's from, and then you can work out which one of the two papers it's in. And then 3 resistors shows in the diagram. Okay. That's nice and helpful of them. Let me flick through, see if I got a copy of past papers that I can use to find it. Yeah, I don't think I do. Right, let's work through them then. Can't have been that one. Could be that one. Could be that one. Could be that one. That one. That one. That one. Could be that one. Could be that one. Right, question 3. Doesn't look like it. 5 volts. No. 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 No, that doesn't seem to match any of the question threes. Oh. No, I don't have access to the latest one either at the moment. I'm doing this from home rather than from in college, so I don't think I've got access right now. So unfortunately, that's not something I'll be able to help you with. And I can ask Google, see if Google will find it for me. No, Google's not giving me much. There's nobody else here, so we can try and work it out. So let's clear this off. And you can tell me all about it. So we've got a battery which has got a 45 volt EMF, and this is connected to, by the sounds of it, a trio of resistors. Make sure that each of these has a symbol for a resistor. There's no line going through any of them to indicate they're a thermistor or anything like that. So what do we know about it? What else does the question say? Have we got any resistor values? What do we ask to find? Could oh, so 750 ohm. Oh, the resistance of R1 and R2 is 50 ohms, 750 ohms. You know what you could do? If you take like a picture of it on your phone and stick that on Imager or something like that, that might work. R1 and R2. Okay, let me label these resistors and you can tell me which one it is. Hopefully my R1s and R2s will match. So I've labelled them 1, 2 and 3. Current. So from what you're saying, I'm thinking we've got 750, 750. We've got 0.03 amps and 0.01 amps. Tell me if that diagram is now correct. Swap. That would be most helpful. Let me have another go at the diagram while you're trying that. I've just rewrote what you've oh, there it is. Not sure the link's working for me. Gotcha, I didn't see the dots were missing. Alright, I see, yeah, okay. So that's a lovely diagram. Where's the actual question? And congratulations on the 2 marks. I'm going to guess it's something like find R1 and R2. So I'll progress until told otherwise. Um, so, we know that the total current flowing through the circuit at this point is 0.03 amps. Kirchhoff's current law tells us that at a junction the total current going in must be the same as the total current going out. Which means that if we've got 0.01 amps coming down here, excuse me, 0.01 amps coming down here, then we must have 0.02 amps coming through this resistor. If we know the current and the resistance, we can find the voltage across this resistor. And the voltage across this resistor must be the same as the voltage across this one. If we can get the voltage and current across this one, we can use Ohm's law to find out its resistance. So using this, V equals IR. This voltage is going to be 0.02 times 750 which is going to come out as let me ask the calculator. $15, so that gives us 15 volts. 15 volts across this one means R is equal to V over I, which is 15 over 0.01, which is going to be 1500 ohms. Now, because there's 15 volts across here, it means there must be 30 volts left over across here. So that's Kirchhoff's voltage law. Sum of voltages in a loop must be equal to the EMFs. So now we've got 30 volts and 0.03 amps, which is going to come out as 1000 ohms. So R1 is 1000, and R2 is 1500. Oh, sorry, I missed that second link. Let me pull that up. Calculate the current I in the 750 resistor, which we just did. Therefore, find the voltage, which we just did. Therefore, find the resistances R1 and R2, which we just did. So there you go. What have you tried to do there? You've got VL equals R2 over R1. No, I haven't got a clue what you tried to do there. I don't see anything there with any resemblance of correctness, unfortunately. That's the answer. Oh, I just noticed my microphone slipped. Sorry if that was a bit quiet. Let me know if I need to go over any of it again. Okay. Um, so you've got to the point where you've identified that the current through the 750 ohm resistor by Kirchhoff's law is 0.02 amps. We also know the potential difference across it by Ohm's law gave us 15 volts. Now, along this branch, when we've got sets of components in parallel, each branch has the same voltage. So because the 750 ohm resistor has got 15 volts across it, the R2 resistor must also have 15 volts across it. Because we know it's got 15 volts and we know it's got 0.01 amps, we can use Ohm's law. R is V over I, so that's the 15 volts divided by 0.01 amps to give us 1500 ohms. Now we can have a look at R1. Because we've got 15 volts across here, Kirchhoff's voltage law tells us that the voltage across the sum of the EMFs must equal the sum of the potential differences. So if we need a total of 45, we've got 15 here, which leaves 30 across R1. So we know we've got 30 volts across R1. We know we've got 0.03 amps passing through it. So using Ohm's law again, 30 volts over 0.03, this time gives us 1000 ohms. Oh, okay. Right, let me run through it one more time. I didn't realise the mouse wasn't showing. Um, I'll scribble on top of it so that you can see. So, our 750 ohm resistor, we know has 0.02 amps going through it, and we know it's got 15 volts across it. You've worked that out in the first two parts of the question. We know that across this potential divider, um, sorry, not potential divider, where we've got this pair of resistors that are in parallel, each branch, so this branch as well as this branch, must have the same voltage. So R2 has a voltage of 15 volts across it. We know the current is 0.01 amps, so when we do 15 divided by 0.01 using Ohm's law, we get 150 ohms for R2. Now, Kirchhoff's voltage law we use to go from, we need a total of 45, we got 15, which leaves us with 30 volts left over as our voltage across R1. We also know the current through R1, that's our 0.03 amps. So we do again 30 volts over 0.03 amps to give us our 1000 ohms as our R1. Thanks for dropping by. Um, there's nobody else seems to be asking any questions, so I'll hang around a few minutes in case anybody decides to chirp up. And if nobody else has got anything to ask, then I've got some freshly baked bread waiting for me. Oh, and none of the Sir stuff.